Hello everyone. This is a short little video clip with regards to a discussion discussion questions that we had during a test week, and one student had to miss the discussion, and he's a good student, so he wanted me to make a little video with regards to what the questions and answers were for this discussion. So here we go. The topic is kinetics, and the idea is that as time goes along, the rate of a reaction or the concentration of a reactant might decrease. And we can look at the rate of that decrease of the reactant concentration to describe the order of the reaction, how quickly it's progressing. Almost always the concentration versus time graph in the beginning is curved. On occasion we might do some mathematics to linearize that, but in this particular question I decided to run just an exponential regression, or what could be a logarithmic regression, and see if I could linearize it, not linearize it, or fit a curve to the data. Indeed, this data is almost too good to believe, because that correlation coefficient is exactly 1, which means it exactly fits the data. That curve exactly fits the data. Calculators, spreadsheets can sometimes do linear regressions or exponential regressions. In whatever case, this data gave me a constant k of 0.00084, which is right here, I believe. In any case, that goes here, or it goes here, or it goes here in your integrated rate law equation. So again, you don't have to know this equation, but it's good to practice it enough that you're sick of it and you can do it. So if I start with 1 molar of H2O2, and the constant of first order decay is this, and you wait 4,000 seconds, you'll come down to 0.0347. How comfortable are you with the logarithms? The inverse of the logarithm is e to the x, or ln of x is e to the x. Look at the buttons on your calculator. The e to the x is the opposite of the natural logarithm function. Yeah. On this one, we're told that we have some curvy data that is linearized by the natural logarithm of A concentration, and that tells me that it's first order in that reactant A. So what I did was I didn't even have to do it, because they told me the slope of the line was negative 0.0297. So that's that. The time is just the time in minutes, this case, and the natural log of the concentration data linearize the graph. And if I know the slope of that line, then that constant k is 0.0927, 1 over minutes. That was given to me, and they told me, well, I decided therefore, since the natural log linearized it, it's first order in A. So I could write it like this, or I could write it like this, integrated law. It's easy to find the half-life from there. You should remember this equation, the 0.693 over k. So if I find k, or actually they tell me k in this case, I can easily find the half-life. Or I can use that constant k and to say, if I start at 0.02 molarity, how long will it take, how many minutes will it take to go down to 0.0025 molarity. And you can see I use my massive algebra skills and a natural logarithm on a calculator to find the time is 70 minutes. I'm going quickly through this because you have the pleasure of going back and looking at this PDF in the old discussion questions folder, and also rewinding the video. On this one, I'm telling you that I did this. They didn't tell me, but you wouldn't be asked to do it on the exam because it just takes too long to fiddle with the data. But if that concentration goes down like this, I try to linearize it by the reciprocal of the concentration data, and lo and behold, that linearized it. And in this case, that slope of that line is the rate constant, and it's also the constant. So this little k, or this little k, came out to 0.000208, 1 over molarity seconds. And if I wait 27,000 seconds and I start with 0.5 molar with this constant, I see that I get down to 0.131 molar. That's kind of a small constant. 27,000 seconds, that's a long time to go from 0.5 to 0.131 molar. So that must be a slow reaction. And indeed, second order reactions are often slower than first order reactions. In this question, what am I told? I'm told a plot of A versus time results in a straight line. Oh, so straight away it's linear, and that means it's zero order, which is also very rare. Zero order means I start with a certain concentration and it decreases linearly to 0. And I wanted to know how long would it take, how much time would it take. They tell me the constant slope of the line, and I start with 0.012 molar to 0.0125 molar. This one's 0. I've solved for t, and it comes out to 313 seconds. Interesting. Again, I don't know if I'd remember this equation, but it's good to think about in practice. This one's not zero order. You see, most of them are not, because the initial concentration versus time is curvy. And then I might try to linearize the data by taking the natural logarithm of the concentration data, and that did not work in this case, but the reciprocal did work. So I decided it was second order. And oh yeah, to find the slope of this line, I went 6, 70 compared to 1, 20. 670, 120. I got a slope of 10, and that slope of 10 means the constant, little k, is 10. Or I could write, since it's second order, I would write rate equals 10 times concentration of A to the second power squared. And this equation, second order integrated rate equation, the constant is 10. If I wait 6 seconds, and my concentration at 6 seconds was 1 over 70, then my concentration at the beginning would be 0.1 molar. Interesting. Math is fun sometimes if you're comfortable with it. It's a struggle if you're not, but it's good to practice. These are the types of questions that we'll ask you on the next midterm coming up this coming week, or next week. Anyways, first order, they tell me the rate law, some constant, this pH3 concentration to the first power. So I pulled this equation out of my hat again. You don't have to remember it, but you do have to know how to use it. So the original concentration, the current concentration at time t, and my constant. I solved for my constant first of all, and then I took it back into the equation to solve for a particular time. How long would it take to go from 2 molar to 0.35 molar if my constant is 0.0115-ish? And the answer is, just do the algebra. Need the natural logarithm button on your calculator. 151 seconds. Alright, we're getting somewhere. And this one, they tell me it's first order, and they tell me at 65 seconds it's gone 45% to completion. But that does mean there's 55% still unreacted. So my concentration at this particular time, 65 seconds, is 55% of what it used to be. 45% of it has been changed or, depleted or gone into something different. From, I don't know what the reaction is. A goes to something. First order tells me this or this, but I like this one in this case because this ratio is 55% or 0.55. So what I have now is 55% left of what it used to be. And again, I solve just with algebra, natural log of 0.55, and my constant, I don't know my constant here. I solve for my constant, then I solve for the half-life easily from there. Interesting algebra, isn't it? How comfortable are you with logarithms? There's another way to do that right here, and that's kind of even a more convenient way sometimes. Depends on how you feel at the particular time with that math. This first order decay stuff also works with radioactive processes, the nuclear changes. So P32 is radioactive with a half-life of 14.3 days. So I took that 14.3 days, divided it into 0.693, got my constant. So this little constant here is 0.0485 reciprocal days. And they're telling me a percent again, 95%. So after, how long does it take to go to 95% completion? Well, that would mean, this is first order decay. This half-life is 14.3 days, and this half-life is 14.3 days, and the next half-life would be 14.3 days. So for first order, the half-life doesn't change, first order processes. So I took that constant into my equation and thought about 95% completed. If I was not 95% completed, that still means I have 5% left over. So this ratio would be 5% or 0.05. And my constant, little k, I determine that from above. Get rid of that e to the x by the natural logarithm on both sides. Takes the natural logarithm of this, take the natural log of that, and that cancels the e to the x. And voila, I solve for t. Yeah, that kind of makes sense. 62 days to go to 95% completion. Because the half-life was 14 days, so it would take more than 14 days to go to 95% completion. I got, what did I get? 62 days-ish. All right, this one, This one talks about a second order. Oh, the half-lives. The half-life here went from 10 in the beginning to 20 to 40. For increasing half-lives, I know it can't be first order. And I assumed it was second order, although it wouldn't have to be second order, but it would be much more complicated if it were third order or some kind of bizarro fractional order that we might see in a catalytic condition. But anyway, if it's second order, then I'll just take the half-life the equation for second order. This is weird, but you can prove it to yourself easily by looking at the integrated second order equation and then take the concentration at a particular time to be half the original. But don't remember this, I would say. It's kind of weird, but it's good to think about the half-life increasing for second order reactions. And in any case, if I start with 0.1 molar and it took 10 minutes to cut in half, then that would mean my constant is 1 over molarity minutes. Then, of course, I take that constant, stuff it back into the integrated equation for second order processes, and voila, I can solve whatever. I solved a couple of times. Let's see, at 80 minutes, the constant was this. My initial concentration is 0.1, and it looks like I get down to, at 80 minutes, 0.011. Or if I only waited 30 minutes, then it would go down to only 0.025. Yeah, this last one's super tricky, but if you think about it, it's kind of cool. There's actually 3 different questions wrapped up here. Let me just go through the first one, perhaps. If I wait 10 minutes to go to 50%, then I know I would have to wait 20 minutes to go to 25% if it were first order. If it were second order, that'd be different. Or if it were zero order, again, a little bit different. But in any case, I assumed first order to begin with. And the clicker question here was enter your answer for the first order case. And so if it was really first order, in part A here, I took... to go to 50% completion, it took 10 minutes. So solve for a little k, comes out to 0.0693 1 over minutes. Then I could take that constant 0.0693 and shove it back into my equation to determine how long it would take to get to the half of a half condition, or 25%, or 1/4 of what it used to be, and the answer is 20 minutes. Well, duh, that kind of makes sense because we already reasoned that out. That the half-life stayed consistent, so it would take 20 minutes. Or if you prefer to go more complicated, we could assume that decay is second order, in which case it would take longer than 10 minutes. I solved for the constant, it came out to 0.1. Then I would shove that 0.1 back into the equation and say it would take about 30 minutes to get to that second window. Or zero order. Perhaps I'll let you look at this at your leisure. For zero order, it's a linear decline from my beginning concentration of 1, and to go down to 0.5 took 10 minutes, and the constant would be 0.05. Shove the constant back in my equation for zero order decay. Start with 1, 0.05 is a constant. How much time does it take to get down to 0.25? 15 minutes. Interesting. Feel free to ask questions of your TA or me. Come to office hours. Hope to see you soon. Thanks for working hard, guys. See you soon.